Ladies and gentlemen, it is my extreme pleasure to welcome you to the very first Essential Technology Concepts webcast. This series of webcasts is intended to provide the foundational technology or concepts, science, principles behind motion imaging and the creation of media and entertainment content. I am your host, Joel Welch, SMPTE's Director of Education, and like to extend very warm welcome to everybody. As you can see, I'm not at my normal office, so the lighting is a little bad. You won't be seeing much of me anyway. You didn't come to hear me talk. I will be helping along with questions, however. I do want to do a little housekeeping before I hand the floor over to your speaker. First of all, these are going to also be 60 to 90-minute webcasts. We have 10 of them planned for 2019. We have speakers identified and invitations out going all the way to the middle of the year. So we're going to be ramping these up and offering them hopefully on a monthly basis right up until about October or so. And again, they're designed to present the fundamental science, principles, and concepts that are the foundation to the technologies and workflows in media and entertainment. We want to make them interactive. And as I always say, in order for them to be interactive, we need your participation. And so that means asking questions. You can ask questions two ways. One is asking them orally, or two, typing them into the question box. These webcasts are going to be free to everyone, and they're intended for early career individuals, people who are just starting out in media and entertainment, but also some of us have learned along the way and done a lot of self-study. So hopefully these webcasts in the series will help fill in any knowledge gaps that we might have. The sessions are recorded for on-demand playback, and those will be available to everybody free of charge. Views and opinions expressed during this SMPTE webcast are those of the presenter and do not necessarily reflect those of SMPTE or SMPTE members. This webcast is presented for informational purposes only. Any reference to specific companies, products, or services does not represent a promotion, recommendation, or endorsement by SMPTE. And I'm very pleased to introduce our guest speaker today, David Long. Many of you may know David. David is the director at the RIT Center for Media Arts, Games, Interaction, and Creativity, also known as MAGIC, and Magic Spell Studios. David, I'm going to remain silent here and turn the floor over to you.
All right. Thanks, Joel. Looking forward to this. This should be fun. I'm appreciative of you guys inviting me to come and talk and be the inaugural speaker in this series. So hopefully we're going to have some fun, showcase a couple of phenomena of your visual systems, and there might be a couple of moments where I make suggestion that you perhaps dim the lights in the room you are, if you can, because some of the stuff shows off a little bit better that way. But be a mixture of some physics, some physiology, some psychology, all the things that make human perception work. And we're going to touch on color and contrast and motion topics. So it's a big ask, it's a big lift for our short time here to get into all the gory detail, but hopefully after this you'll all have an appreciation a little bit deeper for how our eyes and brains work together to communicate these wonderful illusions when we go and consume a cinematic experience or a television experience. So we'll see if I've got the control of the slides. Very good. So let's just jump right into it. The first thing I always like to convey at the beginning of any talk about color or perception is that the human visual system really has a lot of analogy to the artificial or engineered imaging systems we think about being used in cinema. So we will see during the course of this quick talk elements of optics, elements of detection, and elements of processing. And it's kind of in that processing end of the chain where it gets really interesting, and where our interpretation or perception of visual phenomena, where the details of that might manifest a little bit in a confused manner against what a physicist might be looking for, or what someone who actually is designing camera equipment or display equipment is expecting. So to start here, let's talk about where there are strong analogies between the human visual system and with our engineered imaging systems with respect to what I call the sensation of color. So the sensation of color is fundamentally an attribute of spectral physics. So we have to dive into physics a little bit. We have to understand how color comes to be in physics, and specifically how those physical properties outside of our eyeballs combine with the properties inside our eyeballs to allow us to act as detectors of color signals or color stimuli. So in this photograph here on the first slide, I've got my good friend and colleague Jeff Pelz, who's about to be dragged up into the air in a glider. But while on the ground, we got a photograph of him, and the color scientist in me wants to ask the question, why, in standing there observing this scene, does the grass look green? And this is not a botany talk, so we're not going to get into chlorophyll and all that good stuff. We're going to speak explicitly to the observation physics, but it comes from an understanding that the world around us, as far as visual stimuli is concerned, are spectral in nature. So immediately above the picture of Jeff, we have a spectral power distribution, or the power or energy of the light source. In this case, it's the sun and the sky mixed together, or we would call that colloquially daylight. And we see the spectral power distribution across a range of wavelengths associated with the electromagnetic spectrum. Now, we're not going to get too deep into spectral definition and all that good stuff. You've got a cartoon at the bottom of the plot which conveys the distribution of all the various hues that are associated with visible electromagnetic radiation, the wavelengths of that electromagnetic radiation that are visible are between 400 and 700 nanometers. And you can see that daylight is a light source with pretty equal power across all of those. So it's a good example here for starting the story. Now, with that fairly equal distribution of energy, we would refer to the light from the sky and the sun mixed as white light. It comprises all the hues mixed together. And something happens, though, when that white light interfaces with an object. So we have another spectral plot to the right, and it shows wavelength by wavelength the behavior of the material the light is bouncing off of with respect to a y-axis we call reflectance. So where there is low reflectance, that material preferentially absorbs those wavelengths. And where there's a little higher reflectance, that material does what you would think with reflectance. The energy bounces off, and it bounces off very specifically towards the eyeball of the observer. So in this case, the grass is green because across that spectrum, the green wavelengths are the most significantly reflected. The reds, the oranges, the blues, the cyans, those are less significantly reflected. And so the energy available to the imaging system are predominantly green. Now, I've got a picture of an eyeball here. And if we're going to talk about spectral behavior, we obviously need to dig a little bit deeper into the spectral behavior of that eyeball or the human observer. But again, at this point, hopefully it's clear that the color is occurring because of a physical pipeline so far, the light source bouncing off of the object. So how does the observer get defined spectrally? Because it's got to participate in this story as well. We've got a diagram, a cross-section, if you will, the typical human eyeball, and all the major parts you probably learned back in a science class previous in your life labeled. The optical components are at the front, so the cornea is responsible for refracting light. The lens behind it is responsible for refracting light. All of that are mechanism to focus the light from the scene onto the detecting surface. And that detecting surface is generally known as the retina, but we have a very particularly important part of it known as the fovea. Fovea is the central gaze part of the retina. It's the highest spatial detail part of the retina. And when you navigate your world and you stare directly at objects, it's the part of your retina that is doing the imaging for you. Diagram to the right, I have a micrograph, an example micrograph of a human fovea. And we have the various cells in there color-coded. Now, the cells responsible for absorbing the energy from the scene are called cones. And the cones are predominantly responsible for our color vision. Those of you who might remember, again, an anatomy class from your past will know that there are also rod cells in the retinal field as well. But we're gonna focus on the cones because they are predominantly responsible for the sensation of color. Fovea's got some curious facts to summarize. If you look closely, number one, you'll see there are not very many of those cone dots color-coded in blue, but there are quite a few color-coded in red and in green. And while this is not in physics and color science completely accurate to represent it as such, we don't like telling people that our cones are red cones, green cones, and blue cones. They certainly are distributed across the spectrum, and the longer wavelengths for red or reddish colors, middle wavelengths for green or greenish colors, and the lower wavelengths are the blue or bluish colors. And so we associate cone physiology with a reddish, greenish, bluish behavior. It's nice and consistent with how we think of digital imaging systems, for example. But the human observer is just slightly different in a number of important ways, and we'll get into those here just in a second. Now, we saw how the light source in the previous slide was defined spectrally, and we saw how the object was defined spectrally. Clearly, we need a comparable spectral description for the detecting surface, the observer's eyeball, and in this case, the retina of this observer. And I am showing here one representation of that spectral selectivity or spectral sensitivity of the human retina. Now, those of you who have any connection to physiological study, or if you've looked at any of the research done on the actual spectral sensitivity of the cone cells themselves and the biochemical reactions which drive their sensitivity to different wavelengths, there are different ways to represent the spectral sensitivity of human vision. This particular representation is preferred by color scientists because it was the first attempt to define the exclusivity of the different cone types to different spectral regions. And these studies were done back at the turn of the 20th century and were formalized and published in the early 1930s. And as you can imagine, back then, we did not have very good scientific equipment for actually sampling the spectral absorptivity of cone cells or of the biochemical compounds that are in them. And instead, what we did was a little bit of a practical exercise called color matching. We gave observers 3 colored lights of very narrow wavelength band, and you can see listed on the left are those wavelengths. They were about 436 nanometers for a blue, 546 for a green, and 700 for a red. And we asked those observers to mix them in such a way that they could make matches to other spectral colors. Now, if you're trying to match another spectral color that's exactly 546 nanometers, it's easy. You just need the green light. But if you're trying to mix something that is a wavelength other than those 3, it takes a combination. And we recognize this. That's how a lot of imaging displays work. They mix a reddish, a greenish, and a bluish light. Well, once you've assembled all that data and mathematically manipulated it in a useful way, you create what are known as the color matching functions. And the ones we tend to use in imaging applications are the so-called 2-degree color matching functions. There are others, and if you study color science, you'll find lots and lots of variants on this. But the 2-degree standard observer, first published back in 1931, has stood the test of time and is used pretty exclusively in our imaging applications. The curves themselves are designated X bar, Y bar, Z bar. You can see that the color science community did not want to confuse it with red, green, and blue, so we gave it different variable names. And we also tried to manipulate the results of those color matching experiments to give us some fairly particular behaviors in these color matching functions. They've got equal area if you integrate under all 3 curves. They also have a Y lambda curve, as it's called, or the Y bar curve, the middle one, the green colored one, that has been changed to match exactly the 1924 photometric sensitivity function. Now that's an important function. That's a little bit different from color matching functions. That one is meant to communicate wavelength by wavelength which colors of the spectrum appear brightest to our vision. And this is a really important transition in the conversation, because I just expressed a concept beyond simple spectral physics. We're now talking about percept. We're talking about the brain coming into the equation and interpreting the perceived physics in a way that has aesthetic or interpretive or perceived meaning. And the photometric sensitivity function is an expression of which wavelengths in the spectrum, again, appear to us to be the brightest per unit of radiant or physical energy. So if we can summarize our scene here, our use of the human visual system as a camera analogy, we had our light source interacting with our object, and the attenuated spectral energy of the light bouncing off of the object is directed into our eye, hits the retinal field, and these three cone cells, whose color behavior spectrally can be defined in one of many ways, but a most useful way here for color scientists as color matching functions. All of that are the stimuli needed to understand why there is an initial signal to the interpretation of color. All right, so next we're going to turn very quickly to some math. And the particular spectral integration that you would execute mathematically here generates what are known as tristimulus values. So wavelength by wavelength, you would multiply the spectral power distribution of the light source by the reflectance of the object. And then you would further, in a three-part equation set shown on the left, integrate with those three color matching functions. Do a little normalization, and you deliver what are known as CIE tristimulus values. Now, CIE, the acronym is French, but it translates to English. It's the International Commission on Illumination, and is a body that is very concerned with color science and is a good partner in much of the work we do at SMPTE. But their focus is, again, on the ubiquitous color science field. So they talk about just a lot more than just imaging, but we clearly adopt a lot of their practices. So the reason we're doing this integration is because this is now the analogy to every color camera we've ever used. There is an absorption of energy spectrally filtered through the behavior of the color matching functions that becomes the basis of interpretation for color in the human visual system. And the trick to any imaging system is represented here on the next slide. Our goal is always to achieve what's known as metamerism, or colorimetric metamerism. Another name for those tristimulus values are colorimetric values, so as to distinguish them from spectral values like we saw in the first couple slides. So here's a demonstration I like to show, and this is a little bit like the film Inception. You have to figure out which layer of my conversation you're in. But you see a picture of me holding a yellow card, a little homage to my first employer in this industry, Kodak. And on the screen behind that yellow card is a photograph of that same yellow card. Now, when I took this picture, I also took out my spectroradiometer and I measured the light at each wavelength coming off of both the screen, the image of the yellow card, and the yellow card itself. And you can see in the plot on the right, the yellow card itself is the red plot, and that is kind of what you'd expect of a yellowish object under a daylight illumination. I took this photograph in my office during the day with the window open. So the light source, the spectrum, was very similar to the one I showed on the very first slide today. And the yellow object is an object in real life that is preferentially absorbing blue energy. So the wavelengths that it reflects are in the green regime, which, if you can remember from the first slide, is about 500 to 600 nanometers, and the red regime, 600 to 700. And so that plot makes sense. That's what we would expect of a yellowish thing. In comparison, I've got the picture of the yellow card also shown, and its spectrum is a lot different. Yet this photograph is an example of how it really looks the same to us, despite that spectral difference. In the picture of the yellow card, I am on a display that has a red, green, and blue pixel field, and they are responsible for recreating that color stimuli. And not surprisingly, it is the red pixel and the green pixel that are releasing a lot of energy so as to make a metameric match to the actual card. And the color scientists can come along, and with this spectral information, if we integrate those spectra according to the previous equations, and just go back real quick to remind you. So if we take those spectral power distributions either off the screen or off the actual card and integrate them with the color matching function, we'll get an X, a Y, and a Z for both the actual object, which here I've called scene, and the reproduction, which I've called image. And if those two match, it's called a metamer. And metamerism is the secret to all man-made imaging systems. We do not have to match the spectral world. We can defy the physicist a bit by creating color stimuli which look the same in our imaging systems as they do in real life, even if we don't match their spectral behaviors exactly. And so metamerism is the first key to understanding how it is we perceive color, and also how engineers manipulate our design systems to be able to create the facsimile or reproduction of color. Now, beyond this absorption phenomena, beyond this spectral integration, there's a lot of very complex neurological processing that happen. And in another talk at another time, we could probably get into some of those pathways into the brain where the three signals from the long wavelength cones, the mid wavelength cones, and the short wavelength cones, or maybe for today, we can just refer to them easily as the reddish ones, the greenish ones, and the bluish ones. There are a lot of neurological processing that permits human beings to make interpretation of attributes we associate with things like hue. So if I've only got 3 cone types, and one of them is not yellow, why did this card look yellow to me at all? And that interpretation is the domain of that post-retinal processing. Our brain starts to do comparative signal analysis. It looks at the response of the reddish cones and the greenish cones. It detects that both of them are active, and it says, this thing we're looking at right now is neither a red nor a green. It is something entirely different. It's both. It is a yellow. And there are a lot of theories as to the evolutionary processes which led our brains to behave this way. One I always like to tell that makes a lot of sense to people. Imagine you're back in hunter-gatherer days and you've stumbled across a banana tree, and you'd like to decide whether the banana is pre-ripe and starchy and gross, or if it is nicely ripened, the sugars have developed, and it'll be a sweet treat. Clearly, the skin of the banana, when not ready to eat, is green and green alone, and when it's ready to eat, it's yellow. So something in the banana skin starts reflecting wavelength in the red, and if our red cones and our green cones both see that energy, they know it's good, it is not a green banana, and our cones in our brains have evolved to react with an entirely different interpretation. Yellow forms in our mind. So it's color science philosophy to ask what yellow really is if we don't have a yellowish cone, and quite honestly, yellow only exists by the post-retinal processing mechanisms that are at play in our eye. So we want to keep that in mind and recognize that that is in fact how it works. And in fact, it's called staged theory to vision. So there's first the detection, which is the spectral physics, and then there's the interpretation, part of which allows us to differentiate hue and saturation and other attributes. Another really critical part of that interpretation is grayscale, or shadow midtone highlight, the darkest to the lightest, perhaps, energies we might see in either a scene or an image. So all of that is interpreted in that post-retinal processing. So now's a really great time to start a transition. If we were talking only with physicists, so far they'd be extremely happy. We've identified a spectral characteristic of a source, a spectral characteristic of an object, and the spectral characteristic of an observer, or a detection field. And the physicist is happy because they're speaking the same language as perhaps someone who's designing a camera, a color camera. And both are concerned equally about that integration of the spectral energy in the independent channels, red, green, and blue. But as the previous discussion has led us to understand, there's some strangeness that is happening. And it is a combination of physiology and psychology that leads to the field of color science we call either color appearance or color perception. Both are synonymous terms. And quite famously, one of the first characteristics of perception differing from physics that we like to show are the Weber-Fechner models of perception in the luminance versus lightness representation you see on the right. So what does luminance versus lightness mean? Or more appropriately here, I'm sorry, lightness versus luminance, Y versus X. Luminance is the domain of the physicist. It is a measurement of the integrated energy. Low luminance, you're talking about a dark object. High luminance, you're talking about a brighter object, reflecting more energy towards the detector. Lightness, though, is the vocabulary word we associate with the perception of grayness, or the perception of incremental light amount. So you see a series of curves here, and that's because this topic's been studied by a lot of people, and some of the experiments were a little more rigorous and some not so much. I'm going to point out the one that's marked in the middle, called CIE L star. L star is the variable name given to this lightness percept. And what you see is that human perception of lightness is not a straight line reaction to the energy present in the scene. It's more of this power law behavior. It looks parabolic. It's also power law, as we'll see in a little bit. But it's reflective of Weber and Fechner psychophysics. They were scientists who deciphered the mathematical form of human perception. And what they presented was that human beings are really awful at detecting absolute amounts of anything. But our detecting mechanisms are great at observing differences or observing ratios. And so what they proposed was that given a starting signal S, the increment needed to see a difference in that stimulus is constant with respect to the fraction of the original signal. This is just basic percentages, right? So if I gave you a 50% reflecting white surface, and let's say that the human detection of change in lightness was a 10%, I would need to go from a 50% reflector to a 55% reflector, 5 being 10% more than the 50, before I would see a difference. On the other hand, if I had a 5% reflector, which is a very dark one, and I likewise needed a 10% increase, that's only a 0.5 increase. So this behavior is reflected in that power law behavior and is the basis for not just our sensitivity to light and color, it is fundamentally our sensitivity to almost all of the sensory mechanisms that we employ every day, all the senses. So let's keep that one in our brains, in our arsenal, as we kind of step forward and talk about now what we would do to design a motion picture system or any imaging system to appropriately communicate this sense of lightness, if you will, from our scenes all the way to our screens. And I see Joel, which means I might have a question. Except we can't hear Joel.
Now you can.
There we go.
Yes, our guest, Aurora, also known as Rory, would like to ask a question.
Sure.
And Aurora, your mic is open.
Hi, Joel and David. I have a question. In beginning studying imaging, I think vision is often presented as a logarithmic reaction to light, like film has. But I understand that vision is actually more accurately described as a nonlinear response to light versus a logarithmic response that film has to light. Could you elaborate on that a little bit? Have I got that right?
Yeah, sure. That's a great distinction. So I'm going to go back to this curve, and if you can remember from math classes where, say, the logarithm as a mathematical operator was first introduced, the the functional form of the logarithm is to turn any geometric series or proportional series into an arithmetic one. So that Weber and Fechner fraction you see there, that is best described as equal increments when you take its log. So when you talk about, regardless of the signal, it's always a 10% increase that I can actually see a difference. Taking the logarithm of a 10% over 10% over 10% yields a nice uniform arithmetic series, +1, +2, +3, +4, +5. So rather than being confused that why is it when there's a 1% black, I barely need any change at all, versus if it's a 80% highlight and I need a much larger change to see it. If you take the logarithm of those fractions, you end up representing that better uniformity in the perception space, or in this case, the lightness axis. It is true that the equations we use to represent that phenomena are not straight log functions, because Weber and Fechner did a good job of expressing the concept, but there are some slight curve fitting differences. And so the curves we see associated are often also power law curves because they fit the data well. Now, as a trend, a logarithmic function and certain power law functions can be very, very similar. So that logarithmic behavior, or that logarithmic reaction, is really a testament to the Weber and Fechner fraction you see here. And then it's been refined slightly by the groups over the years that have done the good research on fitting human perception against physics axis, or the x-axis here, really, really well. Hopefully that helps.
Did that answer your question, Rory?
Yes, thank you very much. And then if you have any suggestion for further reading on Weber-Fechner, I'd much appreciate that as well. Thank you.
Yeah, sure. Okay, so with our sense of interpretation now a little bit better understood, let's talk about how we're going to design imaging systems to account for some of these behaviors. And oh, by the way, there are going to be some things we introduce next which distort the uniformity of those curves I showed previously. So while we are logarithmic interpreters of light, we can change the logarithmic scaling a bit. You'll see that in just a second. So as a good segue and homage to the question that was just asked, it is common for us to think about scene-to-screen tone management in logarithmic axes. So don't want to belabor the numbers on here too much, but I'm trying to get you all to think about what would the ideal imaging system do to reconstruct the proper perception of contrast on a screen given a known amount of physical energy in the scene. And we're going to take the logarithm and we're going to roughly go on a 3 log unit, and that's base 10 log units for those of you scoring at home. 3 base 10 log units from shadow to highlight. And we are going to contrast that with what I might expect the screen's log luminance behavior needs to be from shadow to highlight. Now, please keep in mind we've got a negative sign here, meaning that the numerical scale for the y-axis is actually inverse of what you might expect. Best way to think about this is if I've got a shadow with a very low log luminance, then I want it to be reproduced on the screen with a very low log luminance. If I apply the negative here, actually to the numbers, you'll see that I am in fact consistent. So dark things here and light things here. And your first impression might be, well, clearly anyone who's making a metamerically perfect imaging system should do so by matching the screen light to the scene light exactly. And that is the last thing you want to do. So let's talk about why. It turns out that human beings are drastically influenced by environmental phenomena when we take in light to our retinal field. So we are not simple cameras. Yes, the light comes in. If we've defined it spectrally, it's integrated with our cones. There's a chance you could think of it starting that way. But we are hugely influenced by the environment we are in, and that's referred to more appropriately as the adaptation state that we're in when we take in that signal. So we're going to go through a lot of fun adaptation mechanisms that describe human vision, And they're listed here. We'll go through them one at a time, so I'm not going to belabor and read off the whole list. The thing to keep in mind, though, is that all of these adaptation mechanisms or interpretation mechanisms in the visual system can be changed simply by consuming our imagery, or for that matter, consuming our original scenes in a different environmental adaptation, okay? And I'm going to give you an example here with the very first one on the list. It's one of the most famous to consider in a classic motion picture workflow, chromatic adaptation. Now, chromatic adaptation generally describes a human being's ability to discount the color of the illumination when interpreting the color or color presentation of the object. If I had a white piece of paper that I knew to be a white object, and I carried it around my home at night when lit by incandescent or rather warmish colored light spectrally, I would still know that that was a white piece of paper despite it reflecting to my visual system an abundance of red energy. Conversely, if I took that same piece of paper the next day outdoors and held it under skylight and observed it there, it would also appear white. I know it's a white piece of paper, and I know that the outdoor more even distribution of bluish, greenish, and reddish wavelengths of energy are a consequence of the change in the illumination, not in the change of the behavior of the object. This is a phenomenon we call color constancy. Human beings know the white paper is supposed to be white, and we interpret it as such. Why did I say this was so important in cinema applications? Well, most of the history of cinema has been photography done on sound stages and studios with tungsten or incandescent lights. Yes, we now have LED, we have HMI, we have other technologies which emulate a daylight spectrum, and of course we film outdoors. But for the longest time in cinema's history, our indoor filming was incandescent filming. Yet, our movie theater projectors and our TVs at home have a very daylight balanced white. So how the heck is it that we as human beings sitting on a set with tungsten illumination could believe the color reproduction is accurate when we watch it reproduced on a display with an entirely different source white, going from that reddish source to that more even spectral source? It's all made possible by chromatic adaptation. So taking that one as the first, let's jump into a bunch of these and speak about how they behave. This is the point in the talk where I will say, if you can, you'll get a little bit more out of these visual examples if you can turn off the lights and not have influences from your environment intruding on what I'm trying to show on the screen. When I teach these at RIT, we turn the auditorium lights completely off, so the only stimuli is from the slides themselves. All right, first one, and proper credit given to my former colleague at Kodak, the legend, Dr. Bob Hunt, who has written so many textbooks on the topic of color science, and I still make my students buy his book as one of their collection. He at Kodak devised this demonstration, which does a fantastic job of communicating chromatic adaptation. Bob Hunt made this a long time ago, so I apologize. That's clearly dated wardrobe, but the concept will still work all the same. So this model is wrapped with a clearly yellow towel. And as human beings, we know what skin tone looks like. We're able to interpret the coloration of skin under incandescent lights, fluorescent lights, daylight. We assume a certain color constancy to flesh and skin color. And that means I can drastically change the lighting on a scene or image that has a flesh tone in it, and it will force you to chromatically adapt and react and to discount any weirdness in the lighting. So in this next pane, I am going to, and this is, if you're seeing the imperfections around the edge, that's because Bob Hunt cut out a cyan filter and very carefully placed it over the towel, leaving the model's face alone, her hair alone, the background alone. It's only covering the towel. And at this stage, the towel should look not its brilliant and purish yellow, but instead it's definitely got a green cast to it. The next thing we're going to do, though, is we're going to place that same cyan colored filter over the entire image. And hard as you might try to think of that towel as anything other than yellow, it probably comes to your vision and your interpretation as a yellow towel. And that's because you know that that skin rendering with that cyan filter over the frame is not a natural rendering for flesh tone, for skin. It is a perturbation that's caused by that cyan filter over it. And so you discount that and you chromatically adapt and you look for color constancy. The towel is yellow. It will be constantly interpreted as yellow. I fooled you a little bit in the middle, but the chromatic adaptation mechanism returns that back to a color constant normal in the right pane when the entire scene is comprised of that overlaid cyan filter. Here's another one that absolutely only works when all the other lights are off where you are viewing this. This is we're going to demonstrate a phenomena known as related color, or the human attention to the percept of brightness. So again, I told you that human beings are lousy at detecting the overall energy of a stimulus, but we're really, really good at comparative assessment. So if you stare at this dot in the middle for a while, it may not appear like a very bright stimuli, but it's certainly neutral. It's achromatic. You don't see any hue in it, hopefully. And it's got a reasonable intensity. There's a reasonable amount of energy coming off of your screen. I'm now going to, in a series of steps, give you something else in the frame to compare it to, and you'll observe a change in your percept of that circle. So I'm immediately going to start stepping through, surrounding it with slightly brighter and brighter reference stimuli. And if you've been staring at that center and allow your peripheral vision to bring in that lighter reference in the concentric rings, you should have gained a percept of a darkening of that center of the bullseye feature here. Now, nothing changed on screen with respect to the energy. So our physicists are fooled at this point. Nothing has changed. The amount of energy coming off the center is exactly the same. But by juxtaposition to that brighter white reference, you're experiencing something known as related color. You compared the energy of the center of the bullseye to the increasing energy to the concentric rings, and your brain said, this is no longer the lightish gray or even dim white I thought it was. In fact, at best, it's a mid-gray, bordering on perhaps even a dark gray for some of you if you're in the right viewing environment right now. And this is important because this is how gray works. Gray does not exist in the world of the physicist. There's no such thing as gray. There's simply gradation in the amount of energy. But in our brains, gray exists when we're able to compare lesser energetic stimuli to a reference that is greater. Now, the other thing that does differentiate human beings from, say, a camera just a little bit is that a camera can have its exposure changed to try to maintain the integrated signal for a fixed energy level. And if I were to have adjusted my exposure in the sequence of images I just showed you here, we could do something to try to maintain the photograph or maintain a measurement of the physical amount of energy. The human being is good at knowing when there is more energy present. In other words, we don't have an exposure setting that fools us into misrepresenting or misinterpreting the amount of energy present. We know full well that even in a well-lit office interior, there is less light than when we walk out into a parking lot. Even if we adapt, even if we let our vision react to the differing amount of total energy, we still retain a little bit of the knowledge that there is a different amount of overall energy. And color scientists call that perception brightness. We are able to assess that some energy is just greater in general, even if it does get, the differences do get subdued a little bit by some of these adaptation mechanisms. Another famous one that's fun, we'll show you next. Here we've got a computer graphic Rubik's Cube. Very, very famously, there is no such emissive color known as brown. Brown is a perceptual phenomena only. And brown is actually orange spectral energy interpreted next to a brighter reference white. So here we've got a computer graphic. We've got in the middle of the two faces here, and the top's clearly illuminated in direct light, and the face that's facing us is in shadow. There's a different percept, right? The stimuli that's in the middle of the shadowed face, we call that an orange, most of us, again, if we're doing this presentation in the right environment. And the top, that's a brown. That's a brown. The irony is, if I slowly fade away the cube and bring the two squares closer together, you've been staring at the exact same energy in both scenarios. So even when the two stimuli are in the same visual field, right, in the exact same frame, your retina and brain working together fooled you into believing that one was a perceptive orange, the other was a perceptive brown. And another of my colleagues, Mark Fairchild, is fond of saying, you know, brown doesn't really exist as an emissive color because no one has ever made a brown flashlight. You cannot project brown light. You can certainly project orange light, and in deference to or reference against a brighter white, you will interpret it as brown, but there's no such thing in a darkened room of turning on a brown flashlight. So the next phenomena I want to talk about is the famous surround adaptation phenomena. So what we're looking at here are curves that remind us of a few slides ago, where we've got the shape of the human reaction, the lightness percept as a function of luminance. And you can see the legend is representing average versus dim versus dark. Those are referring to the adapting field that surrounds the image stimulus. So classic example, I'm in a movie theater. My peripheral vision is consumed with a dark or lights off surround. Whereas if I'm on a movie set or in a studio, I'm probably looking at that same scene that's about to be projected in the theater, but I'm looking at it with a average, or maybe at worst it's slightly dim in the corners of the soundstage, right? It's illuminated a little bit brighter. And what we note is that, yes, human beings, we have a power law response in terms of our perception known as lightness to that actual physical energy luminance, but the curve changes as a function of the environment we're in. And the figure I extracted this from was a little poor in the line style, so I apologize. That's why the red arrows are on there. The legend arrow direction is the same as I'm overlaid on the plots themselves. The conclusion is that in a dark surround, you have a considerably lower exponent magnitude. You have a deeper parabolic bow. That's the top of the three curves, right? And if you were looking at content with an average surround or a lighter field around it, you're going to have the higher exponent in this power law behavior, and that's the bottom of the three curves. But note how it changes. My perception of the lightness as a function of luminance changes simply by looking at that exact same image in three different surround conditions. Now, I could talk to you about this from a mathematical perspective, but my next demonstration shows it really, really well. Here on the screen, I've got three squares. I've got a light, a mid, and a dark, and in one set, they are against a white background, and the other, they're against a black background. The general reference here is that the squares against the black background appear, number one, to be lighter. If you look across, the top light square looks lighter on the right than it does on the left. Same for the mid, the same for the black. The black might be the most compelling, at least on my screen as I'm looking at it right now. There is a associated lowering of contrast as well. The contrast is a little bit less distinct on the right. It's a little steeper on the left. And this is not because the patches are different. It's simply because of the background they're on. And this is the GrossSurround Adaptation phenomena. So if I animate and prove to you, if I bring the right side squares over to the left, they were the same the entire time. Now, this manifested change in contrast is obviously something we have to think about when we design imaging systems. If we're shooting photography on a scene that is a light surround or average surround scene, as most things out in the real world are, but we're going to show them as little rectangular windows in a dark movie theater, our perception of the contrast is going to change. And you can probably come to the conclusion that having an exact metameric match is not the goal. You actually need to compensate for this distinction if you want the pictures to look good. Another phenomena that behaves exactly the same way is the Stevens effect. Our perception of contrast and lightness scales with our adapting white luminance. It's a fancy way of saying the brighter the reference white that we're staring at, the higher the contrast, the darker will neutral series look. The lower the adaptation luminance, the lower the contrast, and the slightly lighter or more washed out the neutral scale contrast will appear. And this is extremely important in motion picture because I guarantee you we all look at content in movie theaters and on television screens that is less luminous, has less white energy than the original scenes. There are exceptions. If we're taking photography at night, that's obviously a low luminance. But if we're in the middle of a sunny day in Los Angeles and we photograph outdoors, the amount of energy that the cinematographer is exposed to there is considerably higher than the image of that same scene. And so when they interpret the contrast of their lighting on set, it will change dramatically when they look at the reproduction on a movie screen at a much lower white brightness. Similarly, the colorfulness or the vividness of colors scale with the adapting white. So the brighter the white, the more colorful things look. The dimmer the white, the less colorful they look. As engineers who design scene-to-screen motion picture systems, we have to boost the colorfulness and the vividness of our colors for presentation in dim white theaters. So again, we see this power law behavior. You might note that the plot here is not like the one before. This is a log-log plot, and I did this on purpose, okay? I want to point off to this next slide. Be wary when you research this data yourself. Look carefully at your axes. Are you looking at these phenomena represented in a linear radiometric scale as in the left, that is luminance normalized in energy units on the x-axis, lightness or L star on the y-axis? Or are you looking at someone who's published their data where both axes are logarithmic? You can see the beauty of a logarithm, as we explained when I answered Rory's question a bit ago. To take the logarithmic representation of the curve on the left, you get these nice straight lines, okay? And it's also important to note that you can see all of the phenomena expressed for either a dark surround or a low luminance, low Y white adaptation in both of these representations. So again, dark surround, low luminance, white adaptation point makes you feel like the content is a little bit lighter, a little more washed out, and a little lower contrast. Though I am always careful to point out, note how in the shadows on the figure on the left, the slope is actually a little bit steeper. It's actually easier to see shadow details when you're looking at imagery in a dark surround or with a low adaptation white. And a lot of people forget that when they try to simply communicate the overall apparent contrast. It is a distributed contrast change. The highlights, the gross contrast is lowered in dark surround and low white luminance, but the shadows are actually stretched out a bit. You can see a little bit better. All right, another phenomena, and go through this one pretty quickly. Human beings have this wonderful ability to segment the scene and react differently. I was secretly making you do that when I had you stare at the Rubik's Cube computer graphic a bit ago, right? You interpreted the orange different from the brown, even though they were both in the same image. We do the same thing with contrast and dynamic range. We have a great ability to take in tremendous range of radiometric energy and adapt very quickly and locally to portions of the scene. If there's a really bright specular reflectance light off of a chrome bumper, we can zone in on that very, very quickly and pull out the detail. Simultaneously, we can move our gaze quickly to a very dark or shadowy area of a scene and pull detail out of there immediately. Imaging systems that we artificially create, cameras and displays, have a tougher time with that. And so one of the tricks we employ in system design to have our imaging systems represent that phenomena of vision is to not produce that straight line response, but instead do what's called rolling the tone scale. So we try to elongate the scene's luminance that is actually rendered to a screen luminance by lowering the slopes on either end and putting in that nice rolled feature. Anyone who studied film knows this curve shape famously. Another thing we have to think about when we're designing our imaging systems are not physiological or psychological at all. They're actually perturbations or errors in the physics. So that's not as interesting for this talk as the others we've spoken about, but we have to be cognizant of flare. Flare light can sneak into our cameras, it can sneak onto our displays, and flare light is the glare, it is the veiling radiometric energy that comes out of the white areas of what we're looking at or what we photographed, and pretty much fills in and washes out any depth in the shadows or the blacks. And anyone who's watched TV in the middle of the day knows that the white end of the scale ends up rendering okay, but the blacks are totally gone because of the pollution of glare or flare light. So we have to highlight all these because they end up manifesting a very intentional scene to screen engineering design in our imaging systems that is not metameric accuracy. Remember that 1.0 sloped curve from a few slides ago, the supposed radiometric ideal? If we did nothing but learn metamerism and physics, we'd all believe that's how imaging systems should be built. But now that you know that environment influences the way we perceive images, it makes sense that the ideal imaging system scene to screen contrast or tone management behaviors are in the green and the red here. We have an increased contrast to try to defeat that low ambient and surround luminance. In a movie theater, we have a lower white point, so we also have to increase the contrast to defeat that. We've got a little exponential kick up in the shadows to try to fill in and defeat that flare. We're a little bit darker overall, right? Both these curves are on top of or above the blue line because we have to combat the lightness percept that comes along with being in a low white level, dark surround environment. And we also have to respect that movie theaters and watching at home are not the same. Watching at home, you probably don't have a fully dark surround. You probably have some lights on in the room, whereas in a movie theater, it's completely dark surround. So the tone reproduction goals for TV are very different than they would be for a theatrical presentation, and we have to take that into account. And I kind of leave this color and contrast conversation by reminding everyone we work in an art field, right? It's wonderful to understand how we could create contrast and colors on a screen that remind us or exact matches to our experience back on the scene. But there's always going to be perturbation. There's always going to be perturbation. And again, homage to my first employer, I think Paul Simon said it best. We are intentionally trying to fool our audience in a lot of cases. All right. One other quick example that's not really represented in the previous, but is fun as well, is a cognitive reaction or a cognitive interpretation. So here we have a picture. This is Pemaquid Lighthouse in Maine. You've visited yourself and are wondering where the heck that is because you've seen it before. And I like to show this one because this was a photograph taken on a lovely sunny day, a photograph taken by my colleague Mark Fairchild. And we like to look at the photograph and ask, if we were to pay attention to the shed here that's right next to the lighthouse, we have materials on the roof and we have a painted side, and we should very naturally interpret that this entire lighthouse, the cylinder, the shed next to it, this little house over here, they're all painted white. They're all the exact same white, right? Whereas the top of the lighthouse is a deep black, and these asphalt roof shingles are, kind of a mid-gray. They're clearly not white like the walls immediately beside. And that is something that we expect from a cognition or a intentional interpretation of the way light falls on objects out in the real world. But again, to our friends, the physicists, who are not thinking as imaging scientists or color scientists, if I isolate the roof here and the wall here, they're actually very similar in their tonality. So in isolation, you would call them both mid-gray. But back on the frame, they are an interpreted darker roof tile and a white wall. Why is the white wall darker in this particular region than the rest of the photograph? It's because it's in shadow. We know how the sun works in real scenes. So our brain comes in and helps us to interpret those physical amounts of energy that are interpreted by the rest of our visual system. Okay, So we're at this 60-minute mark or so. Got just about 5 or 7 minutes that I want to talk about the last attribute of perception that Joel and I agreed would be fun to cover in this first of the series of talks, and that is motion. Because quite clearly, if you've played in cinema very long, you realize that we are not making real motion. We are making what's known as the stroboscopic illusion. We are presenting a series of stills to the human visual system, and we're hoping that that visual system somehow miraculously interprets fluidity and accuracy in the temporal domain. Fancy way of saying we hope things move the way they do on the screen, the way we interpret them to move in real life. Now, there are a couple of phenomena that enable this to happen, and we want to differentiate them because they're not exactly the same. The first phenomena that is important to talk about is persistence of vision. Now, persistence of vision is that ability of the retinal field and the subsequent neurological processing to communicate to the brain that there was light hitting it, even if every now and then the light turns off. This is key in early film projection, as an example. Early film projectors showed a frame of a motion picture film, and then they doused the light with a shutter, so the entire auditorium went black. The film was moved to the next frame, and the dowser was opened again. So there was literally a dark space between the two frames shown. And if we were sensitive to the turning on and off of that light source, we would detect a significant flickering behavior in the stimulant. It turns out, though, if you flash light on and off quickly enough, your visual system fuses and eliminates perception of the dark spaces in between, and that's what persistence of vision is referring to. The particular flash rate, or frames per second, or flashes of light per second, if you will, necessary for that to happen, is known as the critical flicker fusion threshold. And lots of environmental factors influence it. Human beings, if the light is brighter, we can see flicker a lot easier than if the light is a little bit darker. And as we've evolved as human beings, we're actually able to see flicker a little bit better out of our peripheral vision, or the corner of our eye, than the central foveal vision. And all the evolutionary folks who would try to find the causation for that would declare the predator never comes straight at you. The predator is always going to try to sneak up from the side. So our peripheral vision has developed a little faster motion sensitivity. Persistence of vision, though, is not how the stroboscopic illusion works. Persistence of vision is just what's preventing us from seeing the dark spaces between those frames. The ability to detect fluid motion is actually the domain of another branch of psychological interpretation known as apparent motion, with a couple subclasses: beta movement, phi phenomena, and then more complex. Now, this field and our understanding of it is still evolving. So some of the demonstrations I'm going to show you are simplistic, and a lot of good papers have been written recently to debunk that images get interpreted quite as simplistically as these examples I'm going to show, but it still gets the point across. So beta movement, why do we need it? A colleague of mine here at RIT, Malcolm Spall, always liked to show that moving pictures were a stroboscopic illusion, and he's a big basketball fan. So he would talk about watching a video broadcast of a dunk and breaking down the frames and recognizing, hey, there's not a single one of these frames that the ball's actually in the cylinder. It's above from one frame and then is in the netting to the next. So how the heck do you know that the ball actually went through the cylinder? There had to have been a cognitive and neurological association of the subsequent still frames, successive still frames, such that that interpretation would be appropriate. And that phenomena, beta movement, is one of a class of phenomena that are described in human motion processing. So got a long list here, not really going to focus on all of them, but just point out a few, because some of these are more important to cinema than others. The first motion interpretation in the human visual system is real. I'm actually going to really move something in front of you. Now, the cartoons on this plot are meant to express that these studies were done with just single points of light. So if I took a flashlight and made a single point of light and shown it around, really physically moving it, your visual system would keep up and perceive that as actual real motion. If, however, I took a video camera or a motion picture film camera and photographed that moving light, what would be presented on the screen, of course, would be a succession of stills. So why is it that that succession of stills suspends belief and I'm able to interpret fluidity in the motion? Well, if the stimuli is moving short enough distance and there are enough frames per second, I can cognitively, interpretation, perception-wise, fill in the gaps and perceive there to be intermediate positions of the light. That's the apparent beta motion. Now, there's kind of a fun threshold. If I start oversampling and I increase the strobe rate significantly to, say, values that are much, much higher than your typical motion picture frame rate, then I start to induce what's known as phi phenomena, and I'm going to show you phi phenomena in a real example in just a second. The other motion percepts on here are more trivial. Induced motion, we've all been there. For example, the surrounding field moves around us and we interpret motion in the wrong direction. I always teach that, remember when you were in grade school or high school and you're in a big long line of buses ready to pull out from the bus stop, and you peer over and you swear you feel yourself moving when in fact it was the bus next to you moving and you were stationary the entire time. Your visual field was fooled into believing there was motion there. Autokinetic motion, this one's a weird one. It's a scary experiment. If I stick you in a completely dark room and put a stationary light in that dark room and don't move you or it, it'll start dancing on you. And human visual system does not like static stimuli, so it's going to enforce a little kinetics to the stimuli. And then movement after image, I can actually fool you into seeing movement by playing some tricks on your retinal field and conditioning your cone cells to react and make a movement after effect. That's a fun one that some of you might want to look up at some point. Don't have a demonstration for today, but it's pretty cool. So Joel has prepared a couple of videos that we're going to look at. I've actually, I'm going to use an online tool that I think shows off these motion phenomena really, really well, called the Lilac Chaser. And they are going to exhibit apparent motion. The first one we're going to do is going to exhibit beta motion. So the way that the webcast here works, I lose my audio when Joel puts the video up. So I'm going to tell you what to look for. And then after we come back from that, I'm going to tell you what you saw, okay? So you're going to see this picture to the right, and you're going to watch a series of pink dots appear to rotate about your visual field. Now, you want to, for this first one, you don't really need to stare at the X, but the instructions are that you would stare at the X. And I want you to take note of the apparent change in position of the pink dots as this figure rotates on you. So just keep that in mind. Watch for the perception of rotation and the movement of the pink dots themselves. And we'll watch that for about 30 seconds and then I'll come back. So Joel, we're ready to look at the first video. So what you guys should have experienced there, clearly the way this illusion is generated on your screen, one pink light turns off, in the next instant, the position next to it, the pink light turns on. So it's a classic chasing effect. Yet all of us should have experienced that it felt like we were watching a single light, a single pink dot moving very rapidly from position 1 to position 2 and on around the circle. We actually interpreted some intermediate positions. They weren't there for very long, but if you stare at it, you really shouldn't have felt like, oh, that's just one light going off, and then the next position over, a different light is coming on. You really should have felt like it was jumping. And that is the beta movement example. If the distances are small enough, and if the frame rate is right, your brain interprets, these are not two successive still frames, but there was actually motion between those two positions. Okay, this next one is a little bit higher rotation speed, and it induces something called phi phenomena and retinal after image. So I'm going to tell you what you're going to see, but it's going to jump out at you immediately. If you stare at the X, you're going to note that instead of a open gray space like in the figure on the screen right now, you're actually going to see a green dot circling around the pattern. There is nothing on the screen whatsoever that is green. In color science, green is the opposite of magenta. So your visual system, having been over-conditioned to magenta, is actually amplifying the opposite of that to try to, in part, deal with those chromatic adaptation mechanisms and other things which we talked about before, normalize our visual response and our perception. So watch this one, and there'll be a couple other cool things that happen to you that'll blow you away if you haven't seen this example before. So Joel, let's do that one. All right, so I bet for most of you, you saw the green dot circling around, and I bet you also noticed that eventually some of the magenta dots started to go away. So there's a lot of visual phenomena going on here, probably too much to talk about in great detail, but fundamentally the reason you're staring at that X is because your visual system really depends on rapid eye movement and constant surveying of the visual field to update our both neurological and cognitive interpretation of the stimuli in front of us. So when you stared at that X, you were not allowing yourself to gaze across the visual field. And so static parts of the image start to actually fade away. The green dot is there, again, as that after image. And the refresh, or the movement of the circle, was increased because that accentuates the phi phenomena behavior. And that phi phenomena is more associated with higher frame rates, and it's that kind of imaginary or disembodied motion. That green dot didn't exist, but you sure believe that it was a real object circling about the pattern very, very quickly. All right, so last kind of thing to talk about motion perception is that when we go into our world where things are stroboscopic, it is an illusion. And as an illusion, anything we do as engineers to manipulate the parameters, we might be inducing artifacting or just some strange occurrences in that motion presentation and in thus people's interpretation. So clearly, again, we are dealing with an illusion. We are not looking at real motion in our reproduction systems. And because it's so multifaceted, because there are so many modes to the behavior, one of my former students coined a term that I still love and use today. The student, Sean Cooper, he dubbed it temporal texture. This idea that there are lots of parameters which influence the motion percept, especially in the stroboscopic illusion. And we as scientists need to do better about trying to understand them all. So we do some research here at RIT, for example, in a lot of these categories. What is the human sensitivity to frame rates? That influences the percept. How much motion blur in each frame? Because artificially in 3D animation, for example, you can have zero motion blur at whatever frame rate you want. How will that manifest as a percept? If it is a real camera, how do shutter functions impact? Global shutter versus rolling shutter, the good old film shutter, which was a rotary shutter. Also impact of objects moving across our frame while we're taking their picture over time versus camera pans. Pans and tilts change the entire reference field, which gets interpreted by our brain differently than, say, an actor running across the frame from left to right. And then there are all the sampling artifacts associated with doing a shutter mechanism in general. And we tend to think of artifacts in digital imaging, say, with the pixel structure in space, but there's also temporal sampling artifacts that cause us problems. And then, quite frankly, we have to be careful about flicker sensitivity. We certainly don't want to present any images on displays at a lower refresh rate than our flicker sensitivity is able to fuse. We don't want to see those black periods between flickering frames. Good news is most motion imaging display technologies now are what are known as sample and hold, so they don't actually go to black between their refresh, and that solves some of that problem, but we have to be careful of it. So that was my objective for our talk here. I wanted to fill about 75 minutes and give ourselves 15 to follow up if there were any questions. But I certainly appreciate everyone listening, and I hope that some of this was useful in understanding how, in some levels, our sensory mechanisms are just like our cameras, and in others, our brain really makes for some fun accommodation. We really have to engineer intentionally around some of these phenomena, and a lot of times we forget that we have to engineer around those phenomena. So thanks, everyone. I've had fun. Open it up for any questions and turn it back over to Joel.
Thank you, David. I got to say, that was awesome.
Good.
Thank you so much. Angelo says, hot. The moire can be explained. Also, I'd like to remind our guests that you can ask questions two ways. One, the preferred way, is to type in, I have an oral question, and I'll unmute you just like we did with Rory, and then you can ask your question. Or you can type your question into the chat box, the question box, and I'll read it on your behalf. While our guests, I hope, are getting their questions in the queue, both Rory and Jorge asked if you could recommend more source material, more reading. Rory specifically asking about reading on photometric sensitivity function, and Jorge just asking for more source material pertaining to the subject matter.
Sure. So I think a textbook that I particularly like, it's a little bit of a shameless plug for my friend and colleague Mark Fairchild. He's written a book called Color Appearance Phenomena, where the first few chapters are colorimetry in the introduction to color science. So they introduce it as I did, as a physics principle, and then it's a lot of great exposition on the phenomena themselves and a lot of what we just talked about. So I think if you want a one-stop shop, that's an excellent reference, and I'd highly recommend it.
Great, and we're still waiting for questions in the queue. I'm an RF guy, and did a little bit of research in producing a fiber optic course, and they talked about wavelength.
Yep.
When it comes to the propagation of wavelength, what's the relationship between that and frequency? I'm talking time domain and frequency domain.
Yep. So a great fundamental question. Light as a subset of the electromagnetic spectrum travels at a velocity that all electromagnetic radiation travels, and it's a constant in a vacuum, but in real matter like air or other media, water, what have you, it's different, but that is the speed of light. So the 3 × 10⁸ or so meters per second. And it turns out that if you multiply the wavelength of the light by its frequency, you get that speed. So if you wanted to extract the frequency domain, you simply take the speed of light and divide the wavelength out of that.
Great. Thank you very much. Still no questions. Matt said, thanks, David. Excellent webinar. And he's looking forward to the next session. And Scott Daly. Do you know Scott Daly?
I do know Scott Daly.
So Scott says,
Scott's going to correct everything.
He says, can you comment on the Rose-de Vries law, which gives a square root nonlinearity of luminance as opposed to log or cube root?
So I don't think I can comment fundamentally on why that behavior is the particular mathematical relationship. What we have to recognize at the extremes of our vision. So we clip out at the top. We struggle with noise at the bottom. In a lot of regards, our vision, our detective surface, our retina, are not that dissimilar from our digital camera sensors or a film sensor that can only go so far to the brightest brights and the darkest darks. And it's the intrusion of some of those phenomena that change the equation a little bit. And so I always think of it as a little bit better mathematical form, accommodating for those different influences, noise, making it harder to see signal down in the low end, getting to a saturation point, making it impossible to see differentiation of signal at the top end. So that's how I like to think about it. Certainly helps explain why many of our friends in SMPTE and other researchers will talk about the regime change from a log regime change to a gamma regime to the square root regimes, things like that. So beyond them being excellent classifications of the actual phenomena, seeking some fundamental physiological or psychological mechanism for that functional change in those curves, not something I'm intimately familiar with.
Okay, thank you. Good answer. Let's see. Juan Jose said, could you please repeat the name of the book and the name of the author that you mentioned?
Sure. It's Mark Fairchild, and it is Color Appearance Phenomena.
Great. He follows up with, is there a book that you would recommend about color perception psychophysiology?
Again, that one is all-encompassing. There are the other books are probably considerably deeper than I think any of our readers, or I'm sorry, any of our listeners might want to go into. Color Science, The Bible is Wachowski and Stiles. There are a number of vision scientists who have these seminal books, but they get right into it hot and heavy from the first chapter. So I've always appreciated, and speaking with the experience of trying to bring college students up to understand these concepts, Mark's book is fantastic, and I think that's an excellent place to start. But if you are interested in some of those others, more than happy to give you a bit of a bibliography, Joel, and you can share with the attendees if they would like.
Happy to do so. Rory has an interesting question. She says, how do we work up to the hot and heavy stuff?
Yeah, well, we put in a shameless plug for the instructional series that Joel and I are working on, where we're going to deliver these course materials in a little bit more depth. I'm sure that the subsequent webinars, the 60, 90-minute webinars in this series will build slowly but surely. But between those two mechanisms, I think SMPTE is looking out for you, and you should watch your inbox for invitations.
We're trying to. We're trying to. Yes, as David said, we're working on, and actually it's going to be a series of courses if David and I can agree, and I think we can, a series of courses on it's also the essential technology concepts, and we'll go quite deep, and we'll spend quite a bit of time, more time than we have here. And I'm going to go over some of the webcast topics in a minute. We do have a question from Susie. I've read in an article the after image phenomena influenced by overstimulating certain cones. Do you know about this theory?
Yeah, so what you experienced in that very last visual demo, the video, with the green dot is a consequence of that. So overstimulation of a local region on your retina by forcing you to stare at that central black X. The lay way to describe it is it tired out those cones. They were overexerted and so are not quite as efficient. And in the absence of their efficient operation, the color percept that is opposite of them comes out. And so if we've overstimulated the magenta percept, and magenta would be stimulation of the mid or greenish and short or bluish cones. And if you overstimulate them, I'm sorry, I said that, I almost messed that up. The magenta are stimulating the longish or red, and the shortish or blue. And if you overstimulate both and they get a little worn out, the one that comes to the head of the race, because it has not been overstimulated, are the mid or greenish. And so when that magenta stimuli immediately is removed from that portion of your retina, the green or mid cones are fast charging, ready to tell you they see something that's not really there. Kind of a cool effect. That's one way, in fact, if you condition your retinal field to see colors outside of the colors that are even possible to make on certain displays. I wouldn't recommend it because you end up with a little bit of an afterglow, a little bit like staring at the sun for too long, but you can make colors that are not possible on a screen by playing with that effect a bit.
Thank you. Joe has a question. Can you comment on the current debate over film at 24 frames per second, which I see as judder, versus high frame rate imaging, which I see as being more fluid and prefer?
Yeah, so I think it's pretty straightforward that the 24 frame per second standard of film, if you read the history, you know that it's actually associated with the evolution of sound technologies, and it was an agreed to rate based on the engineering systems that were placing sound onto film way back in the first half of the 20th century. And there's, while sufficient refresh to avoid flicker sensitivity and to give you reasonable beta movement, there's nothing about 24 that is the magic boundary between good and bad. It is above a threshold boundary. You can go higher. And when you go higher, your percept changes. And that's what I was alluding to a bit on that last slide. When the refresh rate is increased, you are presenting stroboscopic images in a succession that is faster than it was previous. And so some of those temporal processing pathways in the eye and the brain are subjected to a different task, and that different task materializes as a different perception of the fluidity of the motion. Couple in with that the fact that with a 24 frame per second standard and a 180-degree shutter, everything moving in front of the camera is being manifested with a 1/50th of a second motion blur. Our vision does not have motion blur in that context. It's not the same. We don't have shutters in our eyes. A lot of people ask, well, what's the exposure time of the eye? And that's not such a thing. All of the cells are slightly off cadence with one another, and you can impact their integration of the energy based on how bright your stimuli is versus how dark. So it's not an easy question to answer. But certainly, when you play that in the artificial system at a higher frame rate, you are inducing a different kind of reaction because of this stimuli cadence, and you are in your photography probably having manifested a different motion blur, which all feeds together. That's why I called it temporal texture. It's a lot of interchangeable phenomena.
Okay, we are almost out of time, and I'm going to give you give our guests an idea of upcoming webcasts. However, you know Mr. Mark Shubin.
Yep.
Mr. Shubin has a comment. He says, correct that 24 is related to sound, but it was not an engineering decision. It was based only on existing projection rates.
Sure. Mark and I have had this conversation before. I knew if he was out there, he was going to catch me on a little slip.
Yes. And you will see Mark a little later on this year. He's going to do another webcast for us. But for our guests, I want to let you know about some of the other topics that are coming up in this particular series. You'll probably recognize our next speaker. The next Essential Technology Concepts is March 14th. It's Color Science Fundamentals, and that will be presented by Jacqueline Pitlaris, who I believe is a former student of yours.
She's absolutely a former student.
Absolutely. We also have how cameras and displays work, how speakers and sound systems work. Let's see, production formats, analog, digital, video, audio encoding, and distribution formats. We have one on HDR, 4K, and beyond, and video transport from consumer to professional, DVI, HDMI, SDI, HD-based T, and finally audio, unbalanced versus balanced, XLR, TRS, MADI, AES, embedded, so on and so on. So we do have quite a few webcasts in this series. We will continue them next year as well. I do want to call out the two people who helped us put together this list. There's Jennifer Zaidan and Molly Hill. Hill, who was she a student of yours as well?
Yes.
Oh my goodness. Anyway, so I want to recognize Molly and Jennifer for helping put together the list of topics. They also recommended you, David, as the speaker for this first one. So thank you, David. That was a very informative, very interesting, awesome presentation, in my opinion, and I'm sure our guests found that to be the case as well. I want to thank our guests also for spending time with us today. I will be sending a link to an online feedback form, as we always do, and ask for your feedback. It has been shortened, by the way. The form has been shortened, so you don't have to answer as many questions, but it is important to us that you tell us about your experience. And when you submit the completed form, you'll be automatically redirected to a PDF containing the slides that David presented today. So with that, David, take care. To our guests, safe travels. We'll see you next time on either a SMPTE Technology webcast, Standards webcast, or one of the new Essential Technology Concepts webcasts. Talk to you later, and bye-bye.